funding, which resulted in the current wonderful planetarium that is at Wayne State and the observation dome, both of which you will have many opportunities to check out during the course of the year, and we recommend that you do. But without further ado, Jerry is going to tell us about some cutting-edge science.
Thank you, Diane, and good evening, ladies and gentlemen. So the title of my talk is Pulsar 1913+16 and the Nobel Prize. So let me just spend a minute talking about the name of the pulsar, in particular this number, 1913+16. This is a coordinate which tells us where in the sky we find this object. And you often find for a number of different astronomical objects, numbers following them showing their positions in the sky. So on Earth, we give the location of an object in terms of its longitude and latitude. And in the sky, we do the same. There is a celestial longitude that we call right ascension, and a celestial latitude we call declination. So this particular object is located at right ascension 19 hours 13 minutes at a declination of plus 16 degrees. That's 16 degrees north of the celestial equator. So, as everybody knows, the Nobel Prize in Physics for 2017 went to 3 Americans, shown here, Rainer Weiss, Barish, and Kip Thorne, for their decisive contributions to the LIGO detector and observation of gravitational waves. However, 24 years earlier, there was another Nobel Prize that was awarded, which was related to gravitational waves and their effect as well. So this Nobel Prize went to Joseph Taylor, shown on the left, and his, at the time, graduate student, Russell Hulse. And their award was for the discovery of a new type of pulsar, a discovery that has opened up new possibilities for the study of gravitation. So let me remind you a little bit about a pulsar and its properties. A pulsar is a neutron star, so it's a little tiny star. Typically they're about 10 miles in diameter. They have more mass than our sun, typically, and so matter is very densely packed together. They generally have very strong magnetic fields, so the artist here has represented the magnetic field in terms of these magnetic field lines, similar to what you see representing the magnetic field of the Earth. In many cases, there appears to be a strong beam of radiation, which is emitted from the magnetic poles, as you see. This would be electromagnetic radiation, such as radio waves, sometimes visible light, and other forms. These objects also spin on their axis very rapidly. So this would be the spin axis here, and the indicated rotation. Often they spin several times per second on their axes. So as they spin, this beam of radiation swings round and round through space. And if the Earth happened to be positioned so that that beam, let's say radio wave, swings past the Earth with each rotation, then we get a pulse of radio waves, one pulse for each rotation, hence the name pulsar. So some typical properties of pulsars. They were originally discovered in 1967 by Anthony Hewish and his graduate student Jocelyn Bell. They were from Cambridge University, and a few years later the Nobel Prize in Physics was awarded for that discovery. 1974, went to Anthony Hewish. Unfortunately, they left Jocelyn Bell out, which I think is a bit of a shame. These pulsars are neutron stars. Typical mass might be 1.5 times the mass of our own sun. Again, about 10 miles in diameter, and densities higher than an atomic nucleus. So if you were to go to a neutron star with your teaspoon and scoop out 1 teaspoonful of material and bring it back to Earth and weigh it, what you would find is that teaspoon would probably weigh something like 10 billion tons. So that's the kind of density which we find in these objects. They spin on their axes several times per second is quite typical. So rotation rates of 1 up to maybe 50 hertz is what you would typically find. In many of these pulsars, the spin rate is extremely stable, so that the pulses that come from them are very precise pulses, just like the ticking of a clock. In fact, many of these have just about the same precision as atomic clocks here on the Earth. And finally, I mentioned the magnetic fields. They have generally very strong, typically 10 to the 12th or a trillion times stronger than the magnetic field here on Earth. So Taylor and Hulse were scanning the skies, looking for new pulsars, and they were using the Arecibo radio telescope down in Puerto Rico. This, at the time, was the largest radio telescope in the world. It has a diameter of 305 meters, or about 1,000 feet across. This is the visitor center right here, and I was there on one occasion. There's a very nice viewpoint from right here where you can look down into the bowl. I was there on a tour sponsored by the Planetary Society, and Bill Nye, the science guy, was there as well, who turned out to be quite an interesting fellow. So they indeed discovered this particular pulsar, 1913+16. It's at a distance of 21,000 miles, so it is well within our own Milky Way galaxy. The pulses come with 50-minute millisecond interval between them, which means that the neutron star is spinning on its axis about 17 times per second. However, instead of the pulses arriving regularly, sometimes they come a little early and sometimes they come a little bit late, indicating that the pulsar is moving around a bit in space. Sometimes it's a little closer to Earth, other times it's a little bit further from Earth. So it was very clear soon that in fact it is in an orbit with a companion about some common center of mass. So using the laws of physics and the observational data, they were quickly able to determine a great deal of information about this object. So they know the mass of the pulsar is 1.44 times that of the sun. The mass of the companion is just a little bit less, 1.387 solar masses. They know that the separation between the two objects varies from about 1.1 times the radius of our sun up to about 4.8 times the radius of our sun. So that is typically a few times the Moon-Earth separation in space. So these objects are moving in elliptical orbits, quite pronounced ellipses, and the period, the time for them to go around once in their orbit, is about 7.75 hours. And finally, they measured that the orbit is inclined at an angle of 45 degrees with respect to the plane of the sky. So we know a great deal about this binary pair of neutron stars, even though they're some 21,000 light years away. So the lower picture here, we have an artist's sketch of what the geometry looks like. So this is the neutron star, which is emitting the pulses which we detect on Earth. This is the orbit of the companion. The companion may also be giving off beams of radiation, but they're not directed towards the Earth, so we don't see pulses coming from them. So they're both traveling around a center of mass, which is located approximately here. So in another hour or so, the pulsar is going to move to this point. Its companion is going to move to that point, and the separation between them will be maximum, this distance here. And half a revolution later, the pulsar will move over to here, the companion will move over here, and the separation between them will be this distance, the minimum distance between them. Now, according to Einstein's General Theory of Relativity, massive objects like this moving in their orbits should be giving off gravitational waves, as you see here, and the gravitational wave would take energy away from the system so that the orbit would be slowly shrinking in size and the period be slowly decreasing. And that is, in fact, precisely what Taylor and Hulse discovered. They discovered that the orbit is changing. This just tells us that the ellipses are slowly rotating in space by 4 degrees per year. But more interesting, the orbital period is decreasing by 76.5 microseconds per year. That means that the pulsar and its companion are moving closer together, losing energy, as I indicated. The rate of energy loss is about 7 times 10 to the 24th watts. That's approximately 2% of the luminosity of the sun. And the orbit is shrinking for the pulsar itself. Its major axis, that is the long dimension of the ellipse, is decreasing by about 7 meters per year. Well, it turns out this energy loss can be precisely calculated from Einstein's General Theory of Relativity, and the calculation agrees with the observations within 1/2 of 1%. That was the original data. A little bit later data, they agree now within 3/10 of 1%. So a very good agreement between what was seen and what was predicted by Einstein. So eventually these two objects will merge, as we've recently seen last year, except you shouldn't be waiting for the merger because it's calculated going to be about 300 million years in the future. So this is my final slide, and what this shows you, as a function of time, starting from 1974 when the discovery was made, and in this graph up through about 2004 or so, they show the time at which the objects are closest together. Now, if the objects are not shrinking, or the orbits were not shrinking, the time would always be the same, as determined by the period of revolution. However, because the orbits are getting smaller gradually, they approach closest point together at earlier and earlier times, and that is indicated here as shown. The red points correspond to the observational data, and the curve that you see going through the data, you might think is just the best fit to the data, but that's not the case. The curve is actually what was calculated from Einstein's General Theory of Relativity.
Wow.
That is how good the prediction of Einstein's theory is compared to observations. And the fit is so good, the Nobel Committee decided that these guys, for their observation, deserved the Nobel Prize. And they got it. So, thank you very much.
Hi.
Yes.
I was wondering, is there any mechanism proposed for the cause of the 0.3 of 1% discrepancy between the observed data and Einstein's and the gravitational wave predictions?
Well, these uncertainties are due to, I think, primarily That's a good question, and I don't have a good answer for it because I don't know the details of that discrepancy.
Can I comment?
There is uncertainty in any experimental measurement, and can also be uncertainty in theoretical predictions in the nature of doing the calculations and approximations that you might have to make in doing the calculation. Yes, here's the answer.
No, I think you've got it exactly. I mean, using Einstein's theory to calculate that curve depends on things like knowing exactly what the mass is of each of the objects, exactly what their separation is, and there was a limit to the accuracy that they could measure those things. So that imposes a limit on the accuracy which the theory can predict results. So I'm basically saying what Jerry's saying. Any agreement between any experimental data and any theory always has some level of, it's never perfect.
Wiggle room.
Thank you, Dan. Any other questions? Okay, if not, thank you for your attention.